There's been a strand in astronomy of what you call cosmic surveys, which involve large teams of astronomers really getting together to try to address these fundamental questions about gravity, space and time, dark energy and dark matter. On the dark energy survey, we point the camera at the sky every night. We take a few hundred pictures of the sky, and we take a single picture, we point it at a given point on the sky, and then we'll shift to the next place on the sky we want to take a picture of. So over time, we form a kind of a mosaic that covers about 1/8 of the sky, 5,000 square degrees. The Dark Energy Survey, in some ways, is kind of a successor to an earlier project, the Sloan Digital Sky Survey. And in many ways, the Dark Energy Survey itself is a forerunner to a project that will start in the 2020s called LSST, the Large Synoptic Survey Telescope. That will be a new telescope. It's still under construction now. It's a bigger telescope than the one we're using for DES. It'll be a bigger, more powerful camera. And they will be able to probe even further back in time and over a larger swath of the universe. An analogy is thinking about masons, teams of masons coming together in the Middle Ages to build some cathedral. It took hundreds or thousands of them. It took many decades beyond a single lifetime to construct. And yet they knew they were really constructing something beautiful that would last for hundreds or thousands of years. So I certainly see the Dark Energy Survey and the Large Synoptic Survey Telescope and other projects that are coming in the future as really part of a grand journey to understand the evolution of the universe. To me, the exciting thing is that these kinds of surveys, looking outward in the universe, making larger and larger maps of the universe, more detailed maps that go back further and further in time. So probing the universe on larger and larger scales, nevertheless, we think could be giving us basic information about how the universe operates on the smallest scales. What's the fundamental physics? How do we really understand the nature of space and time and gravity? These data sets are so complex that we really need simulations of cosmic evolution to even understand and analyze the data, let alone interpret them. The computations really translate our theories of dark energy, dark matter, cosmic evolution into observables that we can then go out and test with our observations. "95% of the universe we think is dark energy and dark matter. What they have in common is that they're both dark, they don't emit light, they don't shine, we don't see them directly. But they have very different physical manifestations. Dark matter we think holds galaxies together. Dark energy we think is pushing the universe apart. In 1916, Einstein came up with his theory of gravity called general relativity, which basically says that gravity isn't a force, but rather it's the curvature of space-time. Matter curves space-time around it, other objects move in this curved space-time, and that's what we now mean by gravity. One of the real motivations of the Dark Energy Survey and other surveys is to test Einstein's theory, to really put those ideas to the test by studying the evolution of structure in the universe and studying the evolution of the history of cosmic expansion. I think the evidence for dark matter is quite strong. We see it really explains a number of different phenomena. Dark energy, I think, is our best current hypothesis for what's causing the universe to speed up. But it's still on, I would say, shaky ground, and we really need to do these surveys to understand it better. We don't even know if dark energy really exists as a form of energy, as opposed to something going on with gravity. Maybe what really needs to be replaced is Einstein's theory of general relativity. What we're trying to do with DES, and will subsequently do with LSST, is to push our understanding of the universe back in time, to really understand how the universe has evolved over the last 10, 13, 14 billion years of cosmic history, because that kind of evolution is what we need to really understand the properties of dark energy and dark matter in greater detail. We live on this rather small planet around this ordinary sun, which is, one of billions of stars orbiting around the Milky Way galaxy. These kinds of surveys don't necessarily tell us directly about how our sun formed or how the Earth evolved, but they do give us this broader context of understanding how galaxies like our own formed, and kind of set the stage then for understanding ultimately how we got here.